shown here as HFE into IB, and IE, as you can see, IE is the summation of this two current IB, which is flowing through HIE, and IC, which is nothing but HFE IB. Okay. And if this approximate model is used, then only like the 10% error will be occurring in the estimation of voltage gain, current gain, okay, current gain, and input resistance, RI, RO, etc. Okay, so this is not a bad option. Instead of going a detailed calculation, what we have done in the previous lectures, where we are calculating the various values of current gain, voltage gain, and input resistance, up resistance. But there is a condition. The load resistance RL satisfies the inequality HOB RL less than 0.1 or RL less than about 200 kilo ohm. So using this model, approximation calculation, this model is see that here CC hybrid model is shown here based on that model, approximation model. So we are going to use this approximation model and calculate the various parameters or design matrix of amplifier. The first one is the here common collector configuration. Corresponding to this diagram, this is the simplified hybrid model we started in the last class. So that I didn't say that it is the approximation model, and you see that IB is flowing through HIE as it was shown there, and your HFE IB is here. Now HFE, the IE is the summation of IB plus IE equals to IB plus HFE IB, okay, which is nothing but 1 plus HFE IB. Hence current gain within the approximation model is this minus IE divided by IE, where IE is nothing but some noise is coming. Someone stop your mic. Are you not listening? Are you not listening the noise, or you are just connecting and staying somewhere else? Please don't do that. So using this approximation model, we are seeing that AI is calculated to be 1 plus HFE. Okay, comparing this equation with exact expression which was derived earlier at 840, equation number 840, we conclude that when the simplified equivalent circuit, this circuit is used, the current gain is estimated by less than 10% if this condition is satisfied. HOERL less than 0.1. See, this is the things we derived earlier. It is a detailed calculation. It is not having any approximation. Okay. So, is it not going to be this? See that if HOERL less than 0.1, then AI can be approximated as 1 plus HFE, and hence the error that is occurring is less than 10%. Similarly, input resistance, if you calculate, then you see Ri is the input resistance is what? Input voltage divided by input current. Input voltage is VB, which is connected to the base terminal, and IB is the input current. And you see here what is VB. VB is what? The voltage, and the voltage across this input resistance of the device, and voltage across RL. And what is the voltage developed across RL? The current multiplied by current is this one, 1 plus HFE IB. So this portion is the voltage developed across RL, and this is the voltage developed across this resistance. Okay, that is input resistance. So you get the input resistance as HIE plus 1 plus HFE into RL. Okay. Notice that if Ri much greater than 1 kilo ohm, even if RL is as small as 0.5 kilo ohm, because HFE is much greater than 1. HFE is what? HFE is 50. It is much greater than 1. Okay. So if we substitute equation 54, which we just saw in the last slide, into the equation 41, okay, we obtain this equation. Okay. However, we have just concluded that equation 854 gives too high a value of AI by at most 10%. Means it's talking of the error of 10% only. Okay. Similarly, voltage gain can be calculated, and the voltage gain of the emitter follower, that is common emitter, common collector, is closely unity and is given by this equation. See that equation 842. This equation we derived earlier. Same thing has been written. Same thing has been written here as 1 minus AB equals to HI by Ri. Okay. If, for example, Ri equals to 10 HI, then AV will be equal to 0.9. Isn't it? The statement is correct or not?
Yes, sir.
So if, however, we use an approximate value of Ri, which is 10% too high, then the HIE by Ri is going to be 1 by 11 equals to 0.09, and hence AB will be, voltage gain will be 0.91. Hence the approximate calculation of AV, it gives a value which is only 1% to. Okay, so it's not a big deal. That's what is meaning. This approximate model can be used. Output impedance. From this figure, the open circuit voltage is VS. Open circuit voltage is VS, and the short circuit output is given by this. Okay. Short circuit current is given by 1 plus HFE into IB. Yes, are you getting it? See, IB equals to VS by IE plus RH. That you agree? IB, this current equals what? VS divided by this resistance plus this resistance. Here it has to be open circuited, means this, from this to this resistance is not there. Okay, it is to be open circuited. for finding out the output voltage. And normally that for finding out the output impedance, you connect the external voltage source there. So hence the output admittance of the transistor alone is YO equals to this. Is it going to come this expression or not?
Yes, sir, it will come.
It will come. Okay. So from this equation 843, the exact expression for YO is going to be this. And even if we choose an abnormally large value of source resistance RS, say 100 kilo ohm, then using the typical H parameter value and this table, we find that the second term in this equation 857 is large, is 500 microampere per volt compared with the first term 25 microampere per volt. Okay, so is it that HOE is 25 microampere per volt? Is it? Yes, it is given. See that it is given. For a common collector configuration, it is 25 microampere. And if you put these values from this table, HAP 1 plus HAP is 50. Okay, and HIE equals to what? Is about 1K. Okay, 1.1K. Okay, and sorry, not this here, 1.1K. Okay, and this you have assumed as 100K. So kilo ohm, huh? So is it going to come, this thing? You find that the second term is going to be this 500 microampere per volt. Will it come or not? In the second term, if you calculate, hopefully you'll get the same value.
Yes, sir.
So the output resistance RO of the transistor is 1 upon that YO. So calculate from the simplified model is going to be this RO equals to this. Is an overestimation by less than 5%. So the output resistance RO prime of this stage, taking the load RL into account, is because is the RO and RL will be in parallel. Okay. Now this approximate solution for the CC configuration is summarized here in this table. Okay, and see this RI of this CB is an underestimation by less than 10%. All other quantities, okay, the third row is telling this. All other quantities except RO are too large in magnitude by less than 10%. So error is only 10% compared to the previous calculation. Okay. Now we are going to start a new topic, that is emitter, common emitter amplifier with an emitter resistance. See, emitter resistance earlier was not connected. This was not connected. It was directly connected. Simple C amplifier we have discussed. Now we are connecting a resistance at the emitter terminal. Okay. So what is the advantage of this, and what are the differences in the estimated values of current gain, voltage gain, input resistance, output resistance, etc. That is said that it stabilizes the voltage amplification. That is the first advantage, and it offers a feedback. How it is offering a feedback? That you can understand just simply in this way, that if for some certain reasons a collector current is flowing, higher current is flowing, okay, so a voltage drop across this will increase. This will increase. Voltage level here will be increased or not? More current. So current multiplied voltage is going to increase or not? Yes, Pratham?
Yes, sir, increase.
If that is increasing, then the potential difference between the base and emitter is going to decrease or increase.
Sir, decrease.
VB is going to decrease. If this bias voltage is decreasing, what will happen to the current IB or IC? Obviously, decrease. IC will decrease or not? IC will decrease because if you bias, apply more bias, more current, and less bias, less current. Or you can say if BB is more, your IB is more, okay, and BB is less, IB is less. If IB is less, then you know that IC is what? Beta IB, okay. So IC is also going to decrease. So the very reason is prevented. Reason current increased, that is now helping to stabilize. Could you understand? So this feedback operation is helping to, what kind of feedback it is now then? Yes, tell something. Is it a positive feedback or negative feedback? Anyway, coming to the simple thing you are not understanding. So let me go further. Here it provides the bias stability as we discussed now. It leaves the current gain AI unchanged. So there is no effect on current gain. It increases the input resistance, okay, by 1 plus HFE into RE. It increases the output impedance, and under the condition 1 plus HFE into RE much greater than HI, it stabilizes the voltage gain. Okay, these are the things done by this resistance, emitter resistance connected at the emitter terminal of the BJT in a CE configuration. Yes, understood. These things you remember. Now, approximate solution means that approximate solution means using the approximate model. Okay, approximate solution gives AI equals to IC by IB. Current gain is what? Output current divided by input current. So IC is this one following in this direction, so negative sign, and IB is in this direction. So you get IC equals to HFE IB. IC is equal to C. Okay, IC is equal to HFE IB divided by IB. So IB gets cancelled. You get minus HFE is the current gain of this. So it is not changing, and the input resistance obtained is RI equals to VI IB. VI is across this terminal, okay, and divided by IB. And what is VI? You can understand voltage across here, and HFE RE. HFE RE. I mean current to the load. Okay, in this direction, current is HFE IB. HFE. Sorry, not this. 1 plus this one. 1 plus HFE RE. 1 plus HFE RE. IB is getting cancelled here because this IB is getting cancelled, and you get the we are talking about input resistance, so you should not consider this current through this. Okay, it is not. It is to be current input resistance, and this RE is flowing in this input emitter resistance, not load resistance. So you get this expression, and the input resistance is augmented by this value. Input resistance increases, and with an example, it may be very much larger than HI, And HI was what earlier? HI was what? 1100 ohm or 1.1 kilo ohm. Okay. For example, if R equals to 1 kilo ohm and HF equals to 50, so it is going to be 51, and then 1 plus HFP RE is going to be 51, much greater than 1K. HI was given as 1K in the table here. Where is the table? Yes, this 1K. Okay, 1.1 is used here. So now going further, so AV, from our previous discussion also, we know that AB equals to current gain multiplied by load resistance divided by input resistance. Okay. So putting the values of AI, already you have got the AI. You can, you have got the RI and you have got the AI as minus HFU. You get this expression. Clearly, the addition of an emitter resistance greatly reduces the voltage amplification because it is coming in the denominator. Okay. Voltage gain gets reduced. So somewhere there is no freelance. You are getting high input resistance. Okay. But at the cost of lower gain. You are getting stability in biasing, but yes, you are paying something. That is the loss of gain. We note that if 1 plus HFE into RE much greater than HI is equal to 1.1K. Once again, you are writing. And since HFE much greater than 1, because HFE is equal to 50, then AV can be written as minus RL by RE. Can it be? Yes or no?
Yes, sir.
So look at that. See, 1 plus HFE RE much greater than HI. And HFE is much greater than 1. So it can be, from this expression, you can write this. So subject to the above approximation, AV is completely stable. AV is completely stable. Voltage gain you have lost. I mean, you have sacrificed voltage gain, but you see that it is depending only on load resistance and emitter resistance. If these resistances, material of these resistances are stable, it is not much varying with temperature and all, then you are getting the stability. It is independent of the transistor parameters. See, there is no transistor parameter. Transistor parameters are all the H parameters are the transistor parameter. All the H parameters are the transistor parameter. It is not depending on that. Only care you have to take is value of RL and RE to be material of RE and RL to be such that it is not much varying with temperature. Okay. But we know that that H parameters varies. We have seen the plots also. H parameter varies with temperature and other collector current, etc., etc. So once those parameters not there, it means that from that side there is no chance of voltage gain variation. You're going to get a variation free from the device parameter. From device parameter point of view, it is free from that variation, but only it is depending on the external resistance connected at the load terminal and emitter terminal. Okay, so here the output resistance of the transistor alone with RL considered external is infinite for the approximate circuit of figure 826, just as it was for the C amplifier of section 813 with R equals to 0. Hence, the output impedance of the stage, including the load RL, is RL. Now, why the output resistance is infinite? Why? Let us discuss, you will understand. Okay. Output impedance, how it is calculated, load is removed and you connect an external voltage source. Load is removed and connect an external voltage source here at this terminal, output terminal. And all the voltage sources are shorted. Okay. Voltage sources are shorted and current sources are opened. So you will have current source here. What is called current source? If that is opened, it is removed from here. Then output, I mean to say, resistance is what? This is not there. You have removed and connected it. So it is opened. Impedance is infinite. That's why open circuit is having high input impedance, high output impedance. Yeah. So something is written here. The simplified circuit of this has infinite output resistance because with VH equals to 0 and an external voltage source applied at the output, we find IB equals to 0. This once IB 0 means, and hence IC equals to 0. Okay. Note that when a current source HFE IB is 0, it is assumed to be open circuited. It is removed from this, from here to here. It will be not there. It is not existing as it. However, the true value depends upon the source resistance RS. Okay, source resistance RS. Suppose you have RS lies between. Of course, it may depend on some. If it is shorted, still some current will flow now. If it is shorted, if resistance is there. Now, exact solution. This is the approximate solution we did. Exact solution can be found in the book, and these are the equations you go through from there. Okay. Now, high input resistance transistor circuit and Darlington circuit is also called Darlington circuit. Okay. So it is high input impedance circuit. We are going to discuss now. It's another topic. So first thing we covered now, the approximate model and its application on the C configurations or CC configurations. And then we found the discussion on the topic which deals with emitter resistance, CE with emitter resistance. Now we're going to talk about high input resistance and Darlington circuit. Okay. In some applications, the need arises for an amplifier with high input resistance. At the beginning, we have discussed that if you have the input resistance high, it's better. With an example of mic and speaker. Okay, so it is not unknown to us. We have discussed this thing. So for input resistances smaller than about 500 kilo ohm, the emitter follower discussed in section. Emitter follower means CC is satisfactory. Emitter follower is having high input resistance 144 kilo ohm, so it may be useful, but if it is required that higher than that, then we have to use some other configuration, and that is here called Darlington pair. See, in this circuit, the input impedance, to achieve larger input impedances, and this circuit is used. This is called Darlington pair, and see how it is used. If you look at the Darlington circuit, has cascaded emitter followers, that is correct configuration, with infinite emitter resistance in the first stage, as shown here. Infinite emitter resistance, and this configuration jointly is it is available as a single device. I mean, fabricated by various companies. Summary of this table is shown earlier. So Darlington composite emitter follower will be analyzed by referring figure 830, which will come now. Assuming that HOE RE less than equals to 0.1 and HFE RE much greater than HI. We have from this table I have put here to note something. For the current gain and input impedance of the second stage. Second stage is what? Second stage is emitter follower. Is it not? Is it not emitter follower? Here at the emitter you are connecting the RE. What is the characteristic of emitter follower? The output is taken from the emitter terminal. Load resistance is connected there, which is now, instead of writing ZL or RL, we are writing RE because it is connected at the emitter terminal. Okay, so it is nothing but CC stage or emitter follower, and it's this thing, current gain and RI is important for us, and hence we have put this table here. So Darlington pair will be analyzed now based on this circuit diagram, and as you can see, RE is connected here at the emitter of Q2, and this assumption is made: HFE RE much greater than HI, and from the table 8.7, what we saw right now, for the current gain and input impedance of the second stage. Second stage current gain is found here as IO. IO is this current flowing through this. Okay, IO divided by I2. I2 is the input current at the base of Q2. So it is what? IO equals to 1 plus HFE into I2, isn't it? We have got it earlier, just we are discussing, and I2. So this gets cancelled, you get HFE. Okay. Are you getting this? This one we just discussed today itself at the beginning.
Yes, sir.
Common collector configuration we are discussing with approximate model, and that is what it is. Okay. Now RI2 is input resistance here. Looking at this. Okay, input resistance. Let me put it like this. Looking at this input. Okay, V2. That is the voltage across this point, base to ground, and divided by I2. I2 is the input current. So V2 is what? You put this value here, V2. This also you got and the previous discussion today only, and hence you get it cancelled, you get this expression. The approximate model we just discussed today, and this was obtained as this, finally 1 plus HFE. So the effective load for transistor Q1 is the RI2. I was showing here as the input resistance RI2 here. This resistance we just now got is the load resistance for this one of Q1. Load for transistor Q1 is this one. which is usually does not meet this requirement. That is also agreeing. Author is agreeing that is not meeting. We must use the equation 840 for the current gain of the first transistor, and it is going to be I2, that is the output current here. Okay, that current is this output current is the input current of Q2, which is flowing through the input resistance. Okay, so that input resistance is nothing but the load resistance of this one. So load current or output current of Q1 is nothing but I2. I2 divided by I1. I1 is here. Okay, so putting the value of this I1 and I2, we get this expression. Finally, if this condition is satisfied, then we'll be getting this expression of AI1 current gain of first stage, that is Q1. Overall gain can be written as EI equals to IO by output current divided by input current, and hence it can be written in this way, and we get what? Two stage current is multiplied, or two transistor current gain is multiplied. Hence we can write, putting the values of this thing separately, we get this, and this is written here. Let's see, AI2 we have obtained earlier in the previous slides, then AI1 is obtained here. Put these values and you will get this one, AI, overall current gain. Similarly, we can obtain the input resistance of Q1 as this. Okay, now we are ending this topic, so let us study the concluding remarks about this Darlington circuit. We have already, at the beginning, we have already seen that current gain is not much affected. Voltage gain, what happens to voltage gain?
Decreases.
It decreases. And what other thing happens? Input resistance?
Increases.
Output resistance?
Decreases.
Okay, so this thing already we have summarized, and we have also understood something. What is that? Something else. What is the advantage of using this RE?
Stability.
Stability. Okay, stability is in RE gives stability in biasing, voltage gain, etc. Then we studied this Darlington pair. It is going to give some advantages. This equation for the input resistance of the Darlington circuit is valid for HOERE less than equals to 1 to 1, and should be compared with the input resistance of the single stage emitter follower given by this. If RE equals to 4 kilo ohm and using H parameters of table 8-2, we obtain RI2 equals to 205 kilo ohm for emitter follower and RI1 equals to 1.73 mega ohm for the Darlington circuit. We also find AI equals to 427, which is much higher than the current gain of the emitter follower. So in Darlington pair, we are getting very good current gain. Okay. So these advantages are there. Some. That's why this is available also. Okay. We have assumed in the above computations that H parameters of Q1 and Q2 are identical. That is assumed. But in reality, this is not going to be the case, because H parameters depend on the quotient condition of Q1 and Q2. Since the emitter current of Q1 is base current of Q2, the quotient current of the first stage is much smaller than that of the second stage. So H parameters are not same. Little variation will be there. From figure 8-8, we see that HFE does not vary drastically with current, and hence we have assumed HFE1, HFE2 equals to HFE in the above equations. The high input resistance, the things we are discussing, that is Darlington circuit. The symbol HOE, which increases rapidly with current, refers to Q1 in these equations. So the current in Q2 is 1 plus HFE times the current in Q1. Then HI1 equals to 1 plus HFE into HI2. Using this relationship, we find that the voltage of the Darlington emitter follower is this much. And the output impedance is going to be this. If you take into account these approximations, then you will get this AV and RO as shown here. We conclude from the above equation that the Darlington emitter follower has a higher input resistance and voltage gain less than close to unity. Normally, we have seen in emitter follower or collector configuration, we get very close to unity, here less close to unity. Okay, then the single stage. A major drawback of Darlington circuit is leakage current, which is amplified. Leakage current of first stage is amplified by the second stage. That's why, hence the overall leakage current may be higher, and the Darlington connection of 3 or more transistors is usually difficult, impractical. The composite transistors can of course be used as a common-emitter amplifier. The advantage of this pair would be very high overall HFE, nominally equal to the product of the C short circuit current gains of the two transistors we got. AI1 equals to AI2, so we can understand from there. In fact, Darlington integrated pairs are available commercially also with HI as high as 30,000. Okay. So now I'll go to skip certain things which is not mentioned in the table, syllabus. I'll just these are fundamental things. I'll skip and go ahead to start another topic if time permits. What is the time, Pratham?
So 12:17.
Another 10-12 minutes is there. Well, at least a start. This call is coming. Okay. Hold on. আমার লেকচার চলছে, একটু পরে ফোন করছি, ঠিক আছে? Output stages are a classification of output stages. Now we are going to talk about output stages, particularly for power amplification, power amplifier. Normally, this input stage and intermediate stage C configuration is good for intermediate stage, and we have also seen that which one will be used as output stage also. But here, particularly for power amplifier, we are going to start some topics. Before that, classification of output stages will do. Okay, like output stages are classified according to the collector current waveform that results when an input signal is applied. In this figure, illustrate this is classification for the case of a sinusoidal input signal. The class stage whose associated waveform is shown in figure 1.1a is biased at a current IC greater than amplitude of the signal current IC crate. Okay. Signal current is a notation you try to see. It is little different. It is taken from other book. Okay, notation. Thus, the transistor in a class A stage conducts for entire cycle of input signal. That is, conduction angle is 360 degree. Class A amplifier conducts for complete cycle, unlike class B. Class B, see how much it is conducting. Okay, collected current waveforms for transistor in class A and in class B. Okay. See, as will be seen later, the negative halves of the sinusoidal will be supplied by another transistor. We'll be discussing that in future. It also operates in the class B mode and conducts during the alternate half cycles. In contrast, the class B stage whose associated waveform is shown here in B is biased at 0 DC current. Thus, a transistor in a class B stage conducts for only half the cycle of the input sine wave, resulting in a conduction angle of 180 degree. What is the meaning of that? How we are going to do that? It is going to conduct half cycle or complete cycle. Amplifier, let it be any configuration. Take it as C amplifier. To get output AC current, you have to bias it properly. Isn't it? Biasing means, what do you understand by this term biasing? You have to bias it properly. Normally, we are not showing any battery connection. So far, we have discussed without taking the battery connection diagram, etc. in the figures. What do you understand by biasing? How it should be biased to get a BJT to be amplifier? Any idea, anybody? Ushra, are you there? See, if you are
Yes,
not
sir.
able, yes, tell something on that.
So applying voltage across any two terminals is called biasing.
Okay, then how you are going to bias? How you are going to bias a BJT so that it can be used as an amplifier? We have not
So,
shown the biasing. We have not shown the biasing diagram and battery symbol we have not used. Neither in output side or input side. Okay. And input side means, I mean to say, where we are applying the input voltage, and normally base side or the collector side, output side, okay, in case of C amplifier. So how it is to be biased? BJT is
so
active.
firstly, it should be in the active region. That is, firstly, it should be in the active region for it to work as an amplifier. That is, the base emitter junction should be forward bias and the collector base junction should be reverse bias. Secondly, the input voltage should be greater than the what we call cut-in voltage of the transistor, so that it can be on.
Okay. So cutting at least BB equals to how much?
So,
Cutting voltage you said, na? cutting voltage you
Yes.
said. So what should be the VB cutting voltage
So
in case of C amplifier? For example, take that CE configuration. So in that, what should be the cut-in voltage VBE, VBE, base emitter voltage? Suppose NPN BJT you are taking. Let us take an NPN BJT here. What is the VBE to be applied cutting voltage so that it is anybody else? Yes.
3.7.
Yes, 0.7, beyond 0.7, 0.5 to 0.7. Sometimes, if you read Millman Halkias, it is 0.5 is cutting voltage. Anyway, you said more or less correctly. Okay, point. That depends on the region of operation, saturation and linear active or saturation, etc. Anyway, so suppose if you are biasing in such a way that when you have applied a bias voltage, a battery, nothing but a battery, okay, and this voltage is making just cutting voltage or it's a little above that, greater than, just greater than BBE cut-in. Okay, maybe if 0.7 volt is the cut-in voltage or 0.5 is the cut-in voltage, you have applied just above that. And if your input signal is applied here, that is your mic voltage. Mic voltage that may be 10 millivolt. Okay, and your cutting voltage is 7.7 volt, means 700 millivolt. Okay, so if a 10 millivolt is applied, then when it is positive, I mean positive input is positive cycle, then it's okay. 700 plus 10 millivolt is okay, it will be amplified. But say 10 millivolt less, negative side. So 700 minus 10. So what will happen? If current voltage is not met, then will it conduct and will you get the negative cycle also amplified? I mean to say here, what I mean to say is biasing is important to make the different classes of amplifier. One class is class A, as you can see, 360 degree, means all positive as well as negative cycles will be amplified. In somewhere you see that only it will be conducting or giving output for 180 degree. Then how it is to be done? Even less than 180 degree may be there, or in between 180 degree and 360 degree will be done. So how it has to be biased? That is important here. Okay. So we study about the biasing a little bit for understanding this topic nicely. We'll be taking up from this point onwards in the next class. Okay. Today I think time is ending. Yes, Pratham?
Yes, sir, almost.
Almost. So we'll not go ahead. Little biasing, about biasing you might have studied earlier also. How to be biased so that you can obtain this kind of characteristic of the amplifier. DC biasing should be such that it is sometimes conducting fully for the positive as well as negative signals excursion, positive side. And you can consider this input signal. Here I said 10 millivolt, but if this input signal is coming after amplification of some amplifier, then some pre-amplifier is there. Output, I mean, I'm talking about the output power amplifiers and power output stage of power amplifier. So it means what? Pre-amplifier is there. Some small signal have been amplified previously, maybe filtered also to suppress the noises. Okay, so definitely you cannot just apply the VB. It should be higher or so that the negative cycle of the input signal, which may not be exactly 10 millivolt, but be larger also, is also amplified. Negative half also is amplified. Okay, with this we are ending today. We'll start in the next class. I'm trying to finish as soon as possible. Yes.
Sir, the recordings of these lectures are not available to us.
Recording you need?
Yes, sir.
Then,
Yes, sir.
then I'll keep it. You are not taking the screenshot?
No, sir.
How will you read that book? Are you going to read the book?
No, sir, from recordings.
Recording. It is exactly from book. Okay. Of course.